1 of 0? Also, is it 0 and pi?
When you say tangent to the negative 1,
Inverse tangent.
technically speaking, if you're talking about the inverse tangent as a function, it has a range from negative pi over 2 to positive pi over 2.
Okay, so it's only 0.
It's only 0.
Okay. We get the limit as b approaches infinity from a tan negative 1 and b squared. So we get the equal a and tangent negative 1 of infinity squared.
Numero uno.
Great.
All right, number 1. We're going to look at these. Number 1, for the given sequences, find a recursive rule, an explicit rule. The 9th term, use an explicit rule to state if the function converges. Find the limit of the sequence if the sequence is convergent. Okay, so that's a lot to do. Number 1, let's take a look at this. And let's go ahead and write this. We got 1, 1.5, 2.25, 3.375. So it certainly looks like the function's growing. It doesn't look like we're adding the same thing over and over again either, right? Doesn't seem like we're adding 1.5 plus another 1.5 would be 3. So we're falling short. So this is not arithmetic. So definitely not arithmetic. I wrote that just so I can cross through it.
Yeah.
Is it geometric?
Yeah.
Let's see. 1 times 1.5 equals 1.5. Good. 1.5 times another 1.5. That's 2.25. That's correct. 2.25 times... Sorry. 1.5... You're right. 2.25... times 1.5, that is 3.375. So we have a geometric sequence. Furthermore, we know a few things. We know that the first term is 1, and we know that the common ratio is 1.5. We know that because we kept multiplying by 1.5. Duh. Okay, so now that we have that, we can start looking at a few of the rules. The first rule is the recursive rule. My recursive rule is a1 equals 1, and an plus 1 is going to be equal to 1.5 times an. That's from the notes, of course. B. What about an explicit rule? an should be equal to 1 times 1.5 to the n minus 1 power. Yeah. Let's simplify this a little bit more. Let's simplify this a little bit more. This is 1.5 to... This is 3/2 to the n power times 3/2 to the negative 1 power. So that is 2/3 times 3/2 to the n power. Again, I'm not sure how this would be simplified, or if you need to simplify it for yourself. You should have enough mathematical know-how to get from here to here, though. C, find the 9th term. That's great. You know why that's great? It's because we have the recursive formula now. The explicit formula. So the ninth term should be equal to 2/3 times 3/2 to the 8th power, right?
Well, because then we said we said n, not n minus 1.
You're right, to the 9th power. Yeah, well, I could do a little bit better than that. I can have this as 2/3 times 3/2 times 3/2 to the 8th power, right?
Oh, yeah, because then it cancels.
This is a good idea because, well, it cancels the 2/3. So this is just equal to 3 to the 8th power over 2 to the 8th power. I'm not sure if you have to simplify it a whole lot more than that.
On the back it says that for B it was an equals 1.5 to the n. But so that messed up because they forgot the n minus 1.
Don't know. Let's take a look at D. D, we have, does the sequence converge? What is the limit as n approaches infinity of the general term? Well, that's, yeah, 2/3 times 3/2 to the n power. Thank you. Actually, I forgot the limit here. Darn it. Bless you. Okay, so what's going to happen here if we keep multiplying?
Just going to keep getting bigger.
Yeah, it just seems, is it going to reach a limit, though, is the question. And a few things to think about here with that is, notice the thing that we get multiplied by over and over again is 1.5. That's always going to make the result bigger. So actually this approaches infinity. So does not converge. Yeah, diverges. Now, in years past, we had talked about this, that the only way that this geometric sequence is going to converge is if that ratio is less than 1. Right? Mm-hmm. A geometric sequence only converges if and only if the absolute value of the ratio is strictly less than 1. And that should... if the ratio is negative 1/2, you're also going to get a converging sequence. Okay, any questions on that? Is that it? Nope, there's an E. No, we actually, E is non-applicable, right? Question 2. We have the sequence 15, 13, 15, 13, 11, 9. And it should be pretty clear what's happening with this sequence, right? Yeah, we seem to be subtracting 2 every time. So, adding -2. A. This is an arithmetic sequence. arithmetic sequence. A1 is 15. R is D is -2. Okay. A. Give me the recursive rule. A1 equals 15. AN plus 1 is equal to AN minus 2. Ooh, that might be pizza. Hello?
Yeah. Where's the student be?
Hey, is it Franklin? Yes. Okay, I'll send someone out to the main office. Thanks. Pizza. Yeah. Who's gonna get pizza? We need three. There are 3 of them, so we need maybe 2 people.
I'll get it. You need to learn this. It's fine. You're great.
B. A. That's going to be A1 plus N minus 1D. Substitute that in. AN equals 15 plus N minus 1 times -2. And if you simplify that out, you get, what, 17 minus 2n?
Yes.
17 minus 2n. Unless I did my arithmetic wrong. Okay. C. Find the 9th term. Which is nice because we just did the explicit rule. 17 minus 2 times 9. -1, yeah. Awesome. D. Does the sequence converge? See, the limit as n approaches infinity of 17 minus 2n is equal to 17 minus the limit as n approaches infinity of 2n. What is this limit? This right here goes to infinity. 17 minus a number that goes to infinity? Diverges.
It approaches negative infinity. Because if infinity keeps getting bigger and bigger, so 17 minus a bigger number is closer.
Can you give us one that converges?
Yeah.
We don't know how to do that.
Mm-hmm. Let's do this one. Further study. What about, I don't know.
One half, 1/4, 1/16, 1/32.
Let's say we get this. AN equals 5 minus plus -1/2 to the n. Okay, let's get this one. Okay. So we can get the 9th term. That's not a big deal, right? Let's figure out the limit, though. The limit as n approaches infinity of 5 plus negative 1/2 to the n power. That's going to be equal to 5 plus the limit as n approaches infinity of negative 1/2 to the n power.
I'm carrying things. See, this is for you.
Great, thank you.
And these are red peppers and Parmesan cheese.
Okay, let's talk about this. What happens here with negative 1/2 as n increases? It's going to 0.
Doesn't it alternate from positive to negative because it's negative 1/2?
It goes to 0.
But it goes around.
Oh, yeah, it is because there's one on top of it.
Very well put.
If the numerator is going to 0, it's
Okay, so this limit is this part of the limit. Well, this stays up. Sorry, this part right here goes to 5 clearly. This part right here goes to 0. So the limit is 5. Converges to 5. The sequence
And that answers E, doesn't it?
an equals 5 plus negative 1/2 to the n converges to 5. Okay.
And that's the answer to E. This is what's the limit.
This is further study, so there's no real.
Well, that would be the
Questions?
answer to E. Right?
Yeah.
I suppose, yeah.
If there was another question, would be the answer. So the sequence a n equals 5 plus negative 1/2 raised to the n converges.
Okay, let's try and do a couple more before we start gorging. 3. The second and fifth term of this geometric sequence are 1/2 and negative 32. Let's do that. The second term is. Did you say 1/2 or negative 1/2?
1/2.
1/2.
A5 is negative 32.
A5 equals negative 32. Good. All right, so here's a trick. Here's what we're going to do here. Okay. A5 equals A1 times R times R times R times R. Any questions there?
Goes to the n minus 1 and n 5. 4.
By definition, right? A2 equals A1 times R. Got it? That means A5 is going to be equal to, wait.
A2
A2
R cubed.
times R cubed.
Oh.
What's the question? Find the sixth
Okay.
Okay, negative 32 equals 1/2 R cubed.
Times 2. Negative 64.
Negative. Oh my god. Yep. Oh, but it doesn't matter.
Wow. Okay, let's keep on trucking. We want to find A. Oh no, let's just keep on going. A2. A2 equals A1 times R. In other words, 1/2 is equal to A1 times negative 4. So A1 equals negative 1/8. Awesome. So in other words, any general term is equal to -1/8 times -4 to the n-1 power. I don't think I'm going to simplify that much further than that. Oh, no, they want the explicit rule.
Wait, so what do we do for A and B?
Let's go ahead and
So the common ratio.
let's simplify this.
The common ratio is
Let's simplify this. -1/2, -4 to the n, -1/4.
You said it wrong. You wrote it right.
Wait. What? Just split up.
an
1/32.
(1/32) -4 to the n.
and that's the explicit.
That's my explicit rule. Part A.
Is it
That was part C. We didn't do part A and B.
Wow, what kind of people are you? You have to do everything sequential.
Yes, it's a sequence. It is a sequence.
Is the recursive rule -1/8?
We'll get there.
We did B. We did B, C.
Let's go to part A.
Did we already do D too? Yeah,
Part A.
we did B.
What is the sixth term?
Does it matter which like formula you use for it? Figure it out. Pizza's so scared. There's a microwave. Okay.
To the fifth power,
Isn't it to the sixth?
6th power. Oh, geez. 4, 16.
And
Well, 4 to the 6th is 4096 divided by 32. It is 128. I know.
I said that. So, Mr. Berry, if we do this problem, we should do it in order. We should run the common ratio first, and then find if you need.
Well, because you need the common ratio in order to find the same term. Maybe you should put you should reorder the step, like VA.
Why?
CB.
Part B. Okay. Kind of like what you're saying, what we've been saying here. Like, if you're going to be dealing with these geometric sequences, like it is paramount for you to find the common ratio and the first term. You can't really do anything unless you have those two things. Once you have those two things, the explicit formula and the recursive formula really fall out naturally or easily. Okay? So whatever order you do them in doesn't matter. You're still going to find the ratio and the first term first. That's got to be your first job. Yeah.
Okay, so for the test, if we have like -4 to n-1, do you want us to split it up like you did?
Huh?
Let's say -4 to the n-1, like you have right there. Do you want us to split it up into -4 to the n times -4 to the -1?
It would be nice.
We have to,
So yes or no?
because like I did it and it got it right.
See, it's a really difficult question for me to answer because, you know, mathematically, I don't care which one you do,
Okay.
you know, but I really would like to see this simplified,
Okay.
you know.
Is this going to be multiple choice or short
Could be both.
The answer is exactly the same, so I mean.
Don't get hung up on the answer.
It's not about the answer.
If like I get the problem wrong, it's because I got the answer wrong. Because like that's how I did it.
No, but if she got the answer right, then it's
Let's go to B.
R equals -4.
D. We already did B.
B.
R equals
We already did it.
We did it
R
all.
equals -4.
What is the common ratio? R
-4.
equals -4. C.
We did it again.
He knows. He's
Find
just
the
rewriting it.
explicit rule.
So it's in order.
A and
-1/32.
times -1 to the
Good job, Mindy.
Oh, so this is where you have to separate it.
D. What was the first term?
A to the n
Negative 1/8
Negative 1/8.
Times negative.
times negative 1/8.
Wait, hold on. I thought we were doing the.
The recursive, it's just a to the n plus 1 equals a n times negative 4.
Oh, wait, what?
Boom.
What is it?
That right?
Yes, I think.
Well, that's not what it says in the answers, but then again, it's
The answers like are all wrong. What does it say in the answers?
it's the same thing as the other one where it just switches it around.
Oh. Will you accept either where rather, for the recursive rule, rather than being a to the n plus 1 equals negative 4 a to the n, a to the n equals negative 4 a to the n minus 1?
That's what they do on here.
Okay.
What do you want me to say? Yeah.
One's right and one's
I
wrong.
can't hear you.
I don't get the.
Okay, number 4.
It's like the formula is go. Is it a to the n plus 1?
Oh my god.
That's what it is.
Yeah, okay, but I don't actually get negative 4.
The recursive rule. It's here.
Why should we copy
Does
that?
that say time? Oh, times R. Okay, that's whatever.
Oh,
Okay. Yeah, I think we better pizza time.
Just change for 10.
Oh, I thought you meant like $1.
That's all I got.
I'm picking up my coffee again and Jane. Because I do.
No, I only have one thing. You want any coins? Otherwise it's a nickel. You want any coins there?
These are the worst currency.
I have bad ideas. Pressure. So excited. And then pennies would be the word that I wasted those 2
Gabby, do you want cheese too?
Oh yeah. I got it. And they Abraham Lincoln a lot.
I think you dropped. No, I knew I dropped it.
I totally so like if you're gonna make 1,000 pennies,
How would you feel now? Having taken the love of your life, how could you do that? We're only in math.
Now I need 5 more people.
2,000.
Maybe should I see if I'm actually allergic to pineapple and just eat it?
No.
I'm gonna do it. I just want to barbecue.
I called it. Man, there's people.
How would you find
What? Thank you. That one's for Sarah. I'm afraid of eating it. I'm just gonna give Minnie my pineapple.
Kayla doesn't deserve any. Don't give it to her.
Sarah, would you like a piece?
No.
Okay, Minnie, you want my pineapple?
Yeah. Just put it on.
Like, I want to try it. But like, if you're allergic, it's not a good thing. But I'm not.
you're like,
I have no, I don't think I'm allergic anymore. It was like one time, and I've never ate it again.
paper calcium.
Oh no.
Fine.
I think it's just the stigma.
Feels great. That's
That's chicken. No, it doesn't.
Okay, so I can go get it. So good, Asha.
It's like wine and pizza, and it's like, oh, it has bacon, bacon. And then my pizza comes, and it's like ham. And I'm like, this is not bacon. My dad goes, this is Canadian bacon. And I'm like, Canada does something wrong.
You don't mind?
Yeah, for Valentine's Day, probably John's is like, I don't know,
I don't know. Somebody said no. Really? This one? I really like it.
I really wanted to watch too, and now I don't have to. Did you? Trying to hide from me.
Allergic to pineapple, but you're
Yeah. But it's good.
Okay, smaller.
I literally do used to say, that was a large. Are you allergic? Like, if you eat it, you're gonna like break out in hives. You're not allergic, or like it bothers your mouth.
Like when I was a kid, large pizzas were like huge.
I'm allergic to bananas.
Yeah.
I'm allergic to.
They make my mouth numb.
That's what happens with me with eggplant. Like I couldn't feel my face. I was like,
Remember when those
whoa.
got
It was like for hours too.
to get a rub?
But like I really like eggplant.
Like,
But the only one is like raw. This is cooked. So good.
Ouchie.
oh, that. I was thinking of like a defending lawyer.
I did not physically injure you. Physically injured me. You also hurt my feelings. That means more.
Wait, we're still going?
No, you got a minute.
Okay.
You should chew.
Don't be bad, just like this is like fatted.
I made a joke that I was like, place your bets, seeing his blood or choked on like a piece of food. And then I was like, he's seeing his blood, like, choked on it. And then when he came back,
Is this Mr. McFadden?
and then he did it again, he choked on 2 days ago.
Again? For the second time.
He didn't tell me first class.
I thought you told me you did.
In class?
I got watched about it. Like actually the smaller thing, I think like going back out. Yeah, in the hospital class. And then the other day, he did something and he didn't think about it and he just like swallowed it really fast. And like four fried pizza sausages. I don't have 2 hands. And he served it to the
I'm really scared for when I'm
we
like
went back to
40
the
and
hospital and I
I'm
just got the other piece, pineapple.
I'm trying to think.
Maybe this one's pineapple.
What
Are we doing karaoke?
Oh,
Karaoke.
karaoke. We stay with me.
Man, I can sing.
Oh, rude. I actually like that song.
I can sing Rihanna.
Do it.
Stay.
Yeah, okay. I can play this on the piano. Just to sing 2 chords.
In the style of Rihanna.
Yeah. Look, that guy's actually jumping. It looks like he's hitting himself in the head. They all do.
The same chord song.
Sing it.
I don't know the song.
So like kids pop.
That was horrible, people. That was horrible. Horrible.
I was blowing the roof off now.
Number four. You know what the best part is? You're all going to be on the review, like karaoke.
Yeah. Can we get an A if we know all the words?
That's awesome.
Because I'll just study that.
Okay, so number 4. We have the sequence, and I think what we're going to want to do is write out the first few terms. So an equals -1 to the n power n plus 1 on top of n squared plus 2. Okay, so let's write our first few terms. When n equals 1, an is... Sorry, we didn't need to write all that. We could just say a1. Yeah. a1 equals -1 to the first power, 1 plus 1 over 1 squared plus 2. What is that? Negative 2/3?
Yes. You don't, Sarah.
a2. -1 squared. 2 plus 1 over 4 plus 2.
1/2.
-1/2.
Positive 1/2.
Yeah.
Positive 1/2. Good. a3. -1 cubed. 3 plus 1 over 9 plus 2.
-4/11.
4/11.
I said that.
a3. a4. -1 cubed. 4th power. 4 plus 1 over 16 plus 2.
5/18.
Yeah.
5/18. Good. So let's write this out. an -2/3, positive 1/2, -4 over 11, positive 5 over 18. Okay, this is where we start going into, do you remember that theorem?
No.
You mean that one?
That theorem.
Oh, got it. Yeah. I don't remember that one. No, wait, the one that says that if no, that's not
An
what
alternating sequence on only
Continuous
converges
if
if
you
if a no limit.
From x to infinity.
Oh, that
the limit of absolute value of a and
and
equals
equals
a
Zero.
0. Oh, I remember.
That's what I was thinking.
Was it?
I
Yes.
said this.
Yes, it was.
You said this?
Yeah.
No, you did not.
Yes, it did.
What we have here,
0.
I so badly want to say a failure to communicate, but no. What we have here is an alternating sequence.
Is it absolute value of a of n or a of 1?
an. Okay. So in other words, this is only going to converge if our sequence...
Wait. Does that apply to both geometric and arithmetic sequences?
Doesn't matter what it is, as long as it's an alternating sequence. Only converges...
Wait, that would never happen in arithmetic.
Only converges if the limit as n approaches infinity of the absolute value -1 to the n plus 1 over n squared plus 2 absolute value is equal to 0. Blame Shantae. She said to scroll up.
Shantae, where is she? I'm not Shantae.
Shantae.
Okay.
Brian would like you to scroll up.
Limit as n approaches infinity of the absolute value -1 to the n plus 1 over n squared plus 2.
Didn't we just write that?
That's equal to the limit as n approaches infinity of That -1, basically, if we just get rid of it, we've created the absolute value of the sequence. Because now we have a sequence that no longer alternates positive to negative to positive. Every term of this sequence is now going to be positive.
How do you just get rid of that? Oh, because that's
Can you just get rid of it?
Technically, what you're just saying is that the absolute value of -1 to the n is equal to 1.
Yeah.
So you don't need it.
Oh, so like.
It's like
So you're not really getting rid of it, you're just making it 1.
Did you say that we should try to solve it for the first number and then that's basically.
No, that's not what I said. All right, let's figure out what this limit is. How do I know that this limit is 0? You should have like a couple different ways of showing this is true. Couple ways of showing this. Give me one way.
The exponent.
L'Hopital, sure. What's another way of showing that that's 0?
Exponent of n squared is higher than n.
Exponents. It's another way.
Plug in.
We don't ever directly substitute infinity, but we can just look at the lead terms, right?
Yeah.
Isn't the lead term the same as the x?
So that'd be n over n squared simplifies to 1 over n. 1 over n goes to 0.
Yeah.
Oh, like that.
Okay.
Oh.
Either way, we know that this goes to 0.
Can you explain the exponents, please?
The exponents, yeah. The numerator has a degree of 1. The denominator has a degree of 2. Since the denominator has more power than the numerator, the limit is 0.
And if they're the same, then it's just a coefficient, right? But if the numerator is more than
Infinite.
Why is it still even positive? Why is it
The leading... Yeah, because the lead terms quickly make the other terms insignificant. So, like, for example, if I take a look at the numerator, once n gets to, let's say, 1,000, the difference between 1,000 and 1,001 becomes really insignificant. Same thing with the denominator. Once n gets to 1,000, 1,000 squared plus 2 is nearly identical to 1,000 squared. So the lead terms quickly overwhelm all of the subordinate terms. Okay? Okay, so this limit is 0 since the limit as n approaches infinity of the absolute value of an equals 0. That means the limit as n approaches infinity of just the sequence is also equal to 0. Okay. Two things can happen here. If you get a 0 here, then this limit is 0. If you get anything else, 1, 2, infinity, -5, if you get anything else here on the left, diverges. Got it?
Yes.
6. No, 5. Number 5. All right, we have, find the formula for the nth term. We have 3 halves. We have 6 over 4. Wow, they didn't even reduce it.
No, they didn't. They didn't reduce the next one either.
9 over 12. 12 over 48. Actually, they're doing you a favor by not reducing.
Because they're multiplying
15
by 3 or something. No,
over
I didn't
240.
make that up.
different on the top and on the bottom?
And I think the idea here is let's just write down, let's pretend this is a sequence.
I don't know. She texted me that.
We're going to have to figure out, well, when you have a ratio like this, my recommendation is that you look at the numerator and denominator separately. So in other words, let's take a look at the numerator. 1 and 3, 2 and 6, 3 and 9, 4 and 12, 5 and 15. Okay, so the numerator. That's equal to n times 3. Denominator.
Doesn't it also equal the previous numerator times 3?
That's what. No, it doesn't. So
Previous numerator
because
plus.
9 times
Oh.
3 is not 12.
Yeah, I know. I'm stupid. Never mind.
Denominator.
Plus 3 on those ones.
You're not stupid. So we don't
Denominator times the next. That's 2 times 2, 4 times 3.
Denominator each
5.
number goes.
Oh, doesn't it increase by
N
2?
plus 1 times
Like 2
times
increased by 2.
that value.
So it's times 2 times 3 times 4 times 5.
Multiplied by the nth sequence plus 1.
Yes.
It's whatever.
N plus 1 times that value.
It's n.
Yeah, so that's n plus 1. N plus 1 would be 2 times 2.
But can you give me a formula for n?
For n,
N times.
n plus 1 divided.
Isn't it just n times n squared times 2, but not n times 4?
Here, we can't have a
times
recursive formula.
n equals
Oh,
n
no,
plus
because it-
1
The way
times
an does not allow us to have it.
whatever. N, wait, n equals,
So not n times 1.
equals, I don't know.
I can tell what the answer says.
I know.
Gabby. Factorial.
Yeah.
No, they're just the explanation.
We understand what it is, but we don't know how to put it in terms. 2n factorial.
Good job,
Are we just gonna
2n?
You got exclamation point.
factorial?
factorial.
Yeah, factorial.
Oh. Oh, okay. We haven't done factorials before.
Not since
But did you remember the thing
like
like
the
the
2.
where it's like an exclamation point and then it's like that every number below
So
it.
like 3 factorial is 3 times 2 times 1.
This is a sequence that you're probably going to want to start thinking about, the factorial sequence. 1, 2, 6, 24, 120.
Yeah.
Factorial looks so jolly.
You can do the 3 dots.
Factorial.
You can do the 3 dots just.
Because it's
You
how
always
the
do that.
numerator increases and then the denominator.
So if we can't seem to figure out like what it is, we're just like, you try factorial and see if it works.
It's a good way, yeah.
The person who made factorials really loves that. Like really.
The person who made everything must have really loved it.
6. Six. Determine the sequence converges or diverges. If the sequence converges, and find its limit. So basically, we want to find the limit as n approaches infinity for 2n minus 1 over 3n squared plus 1.
0.
Okay. You should be able to tell me about 3 different ways that you can get a 0 out of this.
Multiply, exponent, and then plus 1.
L'Hopital,
Exponent.
exponent,
First term or whatever you call it.
first term, sure, leading term.
Fifth.
Hmm?
What was the exponent again?
So,
If, yeah.
Denominator is bigger than.
Bottom is bigger than
And if the numerator is
Oh, by the way, does this converge or diverge? Converges.
yay. Did you respond?
Converges to 0. Infinity, yes. No. I don't.
Basically, if it converges, it's going. Never mind.
7. L'Hopital's rule to find the limit if necessary. Limit as x approaches 0 from the right sinks over x cubed. Let's check our indeterminate form. If I substitute 0, I get 0. If I substitute 0, I get 0. That is indeterminate, so it's time for a trip to L'Hopital.
Isn't there a rule that sine x over x?
Okay, the derivative of sine x.
Cosine x.
Cosine x. The derivative of 3x.
You gave us the derivative.
3x squared. Good. Let's check the form. 1 over 0. Oh, that's infinite, right? So now it's infinite. So now we have to figure out positive infinity or negative infinity. Let's see. If I plug in numbers to the right of 0, notice this is to the right of 0. Numbers that are bigger than 0. Will the numerator be positive or negative?
Positive. It changed.
Let's take a look at the denominator. If I plug in a number to the right of 0, let's just say 0.1. Will this give me a positive or negative result? Positive. Okay. If I have positive over positive, we're looking at positive numbers, right? So the limit as x approaches 0 from the right of sine x over x cubed, that's positive infinity. I'm putting the positive there for emphasis. You don't actually have to put it there. Just punch your nose. Punch your nose's nose in the nose. Number 9. Number 9. Limit as x approaches infinity.
Did we already do it?
No. Approaches 0. No, it's not x, it's t. Limit as t approaches 0, 1 over sint minus 1 over t. Let's figure out what indeterminate form we have. Yeah, 1 over 0 minus 1 over 0, which is infinity minus infinity. Not cool. Let's simplify. T minus sine t over t sine t.
So there you just like combine the fractions. Like nothing else.
Huh?
Wait, why is T approaching?
Yeah.
T is still approaching 0. Yeah, I'm just used to writing infinity.
That's why I was confused. I was like, I'm changing it.
Thanks. Good catch. Good catch. Let's get an indeterminate form here. 0 over 0. Take a trip to L'Hopital.
Is that like your new favorite joke?
Yeah. It's incredible that I only figured that out this year.
Really?
Hospital is French for hospital.
Yeah,
It's French for Spanish.
Really,
Patrick.
Oh, hey, wait a minute here. Look at the denominator.
You have to do that
One
product.
minus the cos.
T cosine
One
T
minus cosine t. Oh, right.
minus the plus sine T.
Make sure you use the product rule when appropriate, okay? Can't tell you last time there were so many papers that did not use product rule. Product
No.
rule.
The derivative of negative sine T is cosine T. Negative cosine T.
Let's plug in 0. Let's plug in 0.
1 over, oh no, 0 over.
Cosine of 0 is 1.
Yeah.
You have to do it again?
It's still indeterminate. Take another trip to L'Hopital. The derivative of cosine is
Negative sine.
So sine. 1 plus sine.
oh look, it's a product rule.
I really have to do that? T, negative
Two
T,
sine?
sine T,
Plus
plus cosine T,
plus
plus cosine T.
Shoot. So it's sin plus cos.
good.
It's over 1. It's over 2 or something.
You know what I forgot?
What?
Oh no.
The limit thing.
Oh,
He didn't.
limit.
I read.
Oh wait, I actually put it in.
I did it too about that.
I did it too.
0.
0, yay!
Okay, let's calculate. I think we're good here, right?
Yeah.
It looks like
Oh, yeah. 0 over 2.
0 over
2.
It is 0. Why did I say 1?
2.
2.
0 plus 1 plus 1.
So that's 0.
Happy day.
Therefore, here's your 3 dots. Who wanted that? The limit
I said that.
as t approaches infinity, 0. 1 over sint minus 1 over t equals 0. Man, that does not feel nice.
Did we do You fit it all in one page?
Okay, I think I want to do 2 more questions. Let's do these 2 questions. Let's take a look at which one goes faster. Question 11. x or x plus 1 over x. Which one do you think grows faster? All right, let's bet on that one, okay? Let's bet on that.
No, I did it already. I don't understand. Because I did it already.
X over x plus 1 over x. Okay, I don't like this right here. Not only doesn't it look weird,
1 plus x over 1 over x.
it's like it's a compound rational expression.
Yeah.
We don't like those.
1 plus x squared or something.
So let's simplify that denominator. That's x over x squared plus 1 over x. Okay, that's equal to the limit as x approaches infinity of x over 1 times x over x squared plus 1. Okay. This is all algebra. I'm not actually doing any calculus.
Sure.
I'm sure.
Feels like calculus.
Which is the limit as x approaches infinity of x squared over x squared plus 1. Okay. This limit is equal to 1. Now, you should be able to tell me about 3 different ways why this is 1. Exponents.
Exponents, L'Hopital, and leading term.
That works. It only took all afternoon. That's fine. What happens if we get a 1 here? They both grow at the same rate.
When did we get Oh, I remember that. No, I missed.
Can I have Sarah as my partner on my test? Dibs. Me, Sarah?
You're gonna get Ruby.
But that wasn't one of the things that we did.
You guys have partners?
No, I don't think I was here.
But if we did,
Yeah, can you grow?
Okay. If we go to infinity, then the numerator grows faster. If we go to 0, then the denominator grows faster.
Definitely here for this.
Yeah, let me write this down, okay? So imagine we have the limit as x goes to infinity of f of x over g of x, and we'll say that's equal to L. 1. If L equals 0, then g grows faster. 2. If L is infinite, then f grows faster. And 3, if L is constant, f and g grow at the same rate. Awesome. That takes care of 11. Let's look at 12. Let's look at 12. 2 more. What?
you said we do 12 class.
2 more and then we're done.
12 in class.
No, we said do it now. You said 12, 13, and 22.
Yeah, let's do 12 now, that's it.
No.
Wait.
No, do 14.
14.
Did we do 20?
You're right, I said we do 14. Let's take a look at the antiderivative. E to the 1 over x over x squared dx. Okay, and I'm just looking at the antiderivative right now, and I got to decide which one to use. So there's an exponential here, so clearly this is not a simple integral. That brings me to
Substitution.
a U-substitution.
Yes.
Okay, and if you've been doing this for a while, you've probably noticed that if a U-substitution is going to work, and you have an exponential function, U is going to be that exponent. Okay, so let's imagine if U is equal to 1 over x, what would du be?
Negative 1 over x squared.
Do I have a 1 over x squared?
Yes.
Yes, I do. Okay. U equals 1 over x. Du equals negative 1 over x squared dx.
Why is U 1 over x not 1 over x squared?
Because typically if we use a U substitution with an exponential function,
Oh, yeah. So it's like,
okay. Let's do this. That's that. So this becomes the integral of e to the u negative du, which is equal to negative e to the u plus constant, which equals negative e to the 1 over x plus constant. Great. Good job. Not done yet. Okay, the limit, sorry. Now we have to compute the integral from 0 to the natural log of 2 of e to the 1 over x squared dx. That's equal to the limit as, now do we have a problem with 0 or do we have a problem with natural log of 2?
natural log
Well, do you need to use limit at all?
What do you
Why
want?
can't you just plug in from our antiderivative?
Do you have a problem with 0 or with natural log of 2?
Neither.
natural log of 2.
Take a look here. Do you have a problem with 0 or with the natural log of 2?
0.
0.
Wait, I said that all.
0 from the right side, yeah?
Why from the right side?
It's
Because we're not concerned with the left side because it's only between 0 and 2. Right?
What? No, so repeat that.
We're only concerned with the right side because if it's the integral to area, because we're not concerned with it. Oh. So if you put just a normal 0, it wouldn't make a difference.
I'm not sure if it will make a difference. I'm putting it there because I'm not sure. Equals the limit as a approaches 0 from the right of negative e to the 1 over x from a to natural log 2.
Why do we have
I still don't understand why you can't plug in.
I got it one at a time.
why didn't you just start there? Why did you have to go back and do the integral from
Showing the process.
You just
from
show.
here to
Yeah, because my idea is to do the antiderivative first, and then use the method of antiderivatives with the definite integral.
I'm still confused why you can't just plug in for the integral because the anti.
Because you have something over 0. You want to plug in something over 0? Yeah. Not necessarily. Not with the area.
Wait. What happened to the x squared?
Hmm?
That's the antiderivative. Oh, was that the answer? Oh, this is the antiderivative. Wait, I'm still.
Okay, let's finish this up then. We're taking the limit as a approaches 0 from the right.
Of
Negative e to the 1 over natural log 2. No, we don't need that there. Plus the limit as a approaches 0 to the right of e to the 1 over a
to the infinity. Well, if it's 1 over 0, yeah, wait.
Okay, so we're approaching 0 from the right side, so we're talking about positive values. We have 1 over a, 1 over a, that's 1 over 0, which should approach
Infinity.
infinity e to a very large power.
Infinity.
So infinity. This is just, okay, yeah, so it is infinite.
I just erased all of that because you.
But he's saying that it's not always. So like we have to show that it is. So it diverges. Is that the question? I don't know the question.
Diverges, yeah. Last one. 15.
We never did 20. Okay, guys, we'll do it tomorrow in class.
I'm not going to be here tomorrow.
Integral from 0 to 4.
No.
DR.
Doctor.
Doctor over the square root of burr.
4 minus r. 4. Antiderivative first. Yeah?
Yes.
Antiderivative.
Do you know what we were doing 20?
Antiderivative.
You make it 4 minus r to the negative 1 half. And then you're like, oh. Then you get 1 half.
Okay.
1 half.
Can I integrate this normally?
What counts as normal?
Wait, why can't you do it normally? What's wrong with doing it normally?
We can't do you. What?
Can you just? Oh, I mean, yes,
just
but like
multiply.
usually I just do that in my head. You just know
Oh.
to add it on.
Well,
Dang, girl.
This is what you taught me last year.
She taught me that.
No.
Here, I don't want you to necessarily do this in your head because look, this time you're going to have du as negative dr. And that could produce problems.
No, you know what?
You just move the
This year
negative.
taught me how to live, guys.
You just say it equals negative
You taught me how to appreciate life.
1 half.
She was love.
Okay? All right. Almost done. Negative 1 half plus 1.
1 half.
1 half reciprocal?
2.
2. Okay. So this is 2 negative u to the 1 half plus constant.
Is that negative to you?
Which equals negative 2 square root of 4 minus r. Okay. Very common mistake is to forget that negative. Super common. Now that we have an antiderivative, we can use methods. We can use that in our integral. So now if we integrate from 0 to 4, doctor over the root of 4 minus r. Do I have a problem at 0 or do I have a problem at 4?
4.
Are we approaching 4 from the left or from the right?
From the left.
Left.
Well, why did I write r? I meant b.
Wait, what's to what? Because 4 going to 0, you're going back 0 to the left. Like if it was 4 to 8, you'd be to the right because we're working back. Think of it like 0 to 4, 0 into. Okay, think of it like the number line. To fold that. Yeah. So here's. No, okay, here's 0, here's 4. In between this going to the left, you're going backwards.
Because it's the it's like you're taking the area of a shape, whatever. Let's say it's a triangle, whatever. This is 0. This is 4. Okay? So if you're taking the area of the shape, you're not concerned at all with anything that it has. See, this is the right of 4, right? This is the left of 4. So you're only concerned with what's going on.
Why are you plugging B in?
Does that make sense? Yeah.
I will.
No, but why are you replacing 4 with B and not replacing 0?
That makes so much sense. Thank you.
Because 0 doesn't give me a problem. 4 minus 0 is 4. Or square root of 4 minus 0 is the same thing as 2. There's no problem there. However, if I put a 4 there, I get the square root of 0. I have a problem because it's going to be dr over 0. That's not good. All right, let's start simplifying this then. We're almost done. Hey, everyone. B is going to approach 4 from the left. Do I have any problem plugging in B now? No. This gives me 0.
0 plus 2, 4.
6, 8.
Dude, we appreciate it. Brian.
So you would just plug in over there on the left.
I know.
If we don't break 4 from the left, are you going to count us wrong?
No, not necessarily. You should, though.
I mean, I'll try to remember to do it. I will put my best effort.
So happy. Why is it coaching on the left side?
Oh, they kind of went over it ad nauseum over here. Yeah. Okay, everybody. It's a wrap.